those for you, but I want to encourage you to really practice this stuff. And if you can practice it to the extent that I cover it in class, I'm not going to be just throwing a bunch of surprises at you. So it's really a matter of taking care of business. If you take care of business, you understand the basic principles, you're not trying to memorize the equations, but you're really understanding what's going on, then you've got a really decent opportunity to do well on this exam. And so you're going to get a lot of problems that will be like midterm-like problems in lecture and in our problem-solving sessions today and tomorrow. And then I also want to introduce today Gauss's law, which is chapter 23. So today we'll finish up chapter 22 and start chapter 23. Now, chapter 23 will not explicitly be on the midterm, although you might see a definition or something, but I'm not going to have the homework from chapter 23 be due a week from today. But the other homework is due, and along with that, you'll have the problem-solving sets that are associated with the lab, and that'll be graded as a lab with extra credit. So are there any questions about where we're at right now in relationship to the midterm?
Is it going to be like the same format as other midterms? The 60 stuff? Okay.
Yeah. I'll put here 23, but just very basic, like a definition, but not something that you need to work through the homework problems for. But I will be covering that pretty much exclusively on Tuesday. So you could see something on it, but there's an overlap between 22 and 23. And so I think it'll actually help you get ready for the midterm to see some more general ways of calculating electric fields, which is what 23 is all about. And maybe hopefully give you a better idea as to how to work with electric fields and what they are. That's really a big deal, is knowing what they are and how they are useful to us.
So homework's coming on Wednesday,
Yeah. Yeah, and that's on the home page. I may have to revise the time frame on that, because originally that was a week from Tuesday, but because of the slack trip, we're moving the midterm up to next Thursday. Okay, any other questions? All right, last time, and I didn't get a chance to make a copy of this for you last time, but this is kind of what we covered. We looked at the charged ring problem, and we saw that complementary pairs of charges can give rise to little electric fields, and associated with those, we can integrate all those little electric fields to give us the total electric field. And so this was the result that we got from last time for a charged ring. This is x. And let's make this distance here. No, okay, we got an r there. So with respect to big R, which is the radius of the ring, we had an electric field that looked like K, big Q, where Q is the total charge on the ring, uniformly distributed across the ring, times x divided by the square root of x squared plus the radius of the ring squared, r squared, times some unit vector that points in the I hat direction. So the E then is the sum total of all the little dE's, and the dE's that survive are the cosine theta components of the dE's. So if this angle here is theta, then that makes this angle here theta. That allows for us to get our radius r from each of the little dq charge elements to the point on the ring. And so, this is not square root, this is so that was the result that we derived from last time, and it's kind of redone here. One thing that I wanted to add to this is that, and also recall that we looked at what would happen if you put a charge at the center, and how could we adjust that charge to make the electric field 0 at a point x on the ring. From there are some other applications of this that I wanted to look at. First of which is, what would happen if x is small but not quite 0? What would we get? Well, in other words, let's go to here. And then let's place a charge at that small value. And let's say that this is a negative charge, whereas this total charge on the ring is plus q. And so what would be the direction then of the force on little q if we're at some kind of smaller distance x away? If this is big Q, what would be the charge, what would be the what would be the sign of the charge to get an attractive force?
Negative.
Be negative. Okay, so we would want this to be a negative charge Q, and if that's the case, then if the electric field is pointed in this direction, what would be the direction of the electric force? To the left. Okay, remember, F is QE. So these are all super basic relationships that I hope you've drilled in, and that you're not just kind of, well, I kind of forgot that, because that's not going to be helpful with all the other things that you have to think about in these problems. Okay, so F then is the physically measurable force that we can get from placing a charge into that electric field. So that's a critically important equation, just conceptually, that you understand that this is a charge that's put into this field, but this field is caused by some other charge. And so when we put that there, we're going to get a force that's going to point inward like that. And so what we might expect to happen is that that charge would start to speed up. Let's say it's constrained to move along the axis. Okay, so that charge would speed up until it gets to here. What would the force be here? 0. Okay. Now how do we get that? Well, if we look at all of the little dq charge elements, we can always break them up into complementary pairs. And so that means that if this is a charge minus q right at the center at x equals 0, so now I'm looking down this thing. So here I am looking like that. And what I'm seeing is that each one of these dq charge elements is going to pull equal and opposite on the charge minus q and give rise to a 0 value for the force. Now what's the direction of the electric field when we go to negative values of x?
Still towards the center, so to the right.
It's going to be this way, isn't it? The electric field? Because here, the little charge elements are going to shoot off DEs just the same way. So it has the same kind of symmetry here. Remember that the electric field lines always point away from positive. So that means that it's going to have the same kind of symmetry, but it's going to be pointed in the negative x direction. Is that what we see when we look at this expression here for the electric field? And we go to negative values for x. Yes, because this is going to be a negative squared, but this negative is going to maintain itself, and so we'll have a minus I hat direction. Okay, but physically you can look at it and you can see that it just has that same symmetry, but pointed in the opposite direction. So that means that the force, if this charge were to speed up to here and then have a maximum speed, then what's going to happen to that speed as it passes through the center point?
It's going to slow down.
It's going to slow down. Good. And so what does this kind of remind you of?
Simple harmonic.
Simple harmonic motion. Now, to show that it's simple harmonic motion, you have to be able to set up an equation that looks like this. F equals minus kx. If we can't get it to look like that, then it might be a restoring force, but it's not simple harmonic motion. Simple harmonic motion must obey this equation. What does that mean? Well, it means this can't be an x squared or an x cubed. It's got to be a linear restoring force, so that if you double the force, you double the distance. Okay, so simple harmonic motion must be must have a linear restoring force. Which just means that it's proportional. The force and the x plot out to a straight line, and the slope is the spring constant. And if that's the case, then when we take two derivatives of this, we can get something that looks like x equals a times the cosine of omega t. That's what we got earlier this semester. Okay, so how can we, but does this look like that? Well, up front it doesn't really look too much like that, does it? Because we've got an x squared term down here in the denominator. We do have an x term in the numerator. So that kind of looks like this, but that x squared term kind of messes things up. But if we look at the limit of small x, so that's what we're talking about here, small x, then what we have is the x squared term in the denominator becomes small. If x is less than r, then x squared is much, much less than r squared. And so that means we can throw it out in the denominator. Okay, but we don't want to throw it out in the numerator. And so this is always a little bit of a dicey thing, is if you've got x's in the numerator and denominator, and I'm throwing it out in the denominator, then why am I not throwing it out in the numerator too? Well, the reason is that in the denominator, it's small in relationship to this other term that's being added to it. Whereas up here, it's just by itself. So if you throw it out in the numerator, you're throwing out the whole problem. Then it's just 0. Okay, 0 over 0, which is actually indeterminate form. And so what we want to do is just throw it out in the denominator, because x squared is way smaller than r squared. For example, let's say that r was 1 meter and x was 100th of a meter, a centimeter. Then x squared would be 1/10,000th of r squared. Because r squared would still be 1, but 1 over 100 squared is 1 over 10,000. So this would be like 1/100th of 1% error by throwing out the x squared term. So that's why we can do it. That's why we can justify doing it. And so f is equal to minus kx, but it's also equal to qe. So let's put that all together here. F equals, and it's going to be negative, because the charge is negative. That makes it a restoring force. With Hooke's law, it's got to be a restoring force. If this were a positive value for q, then there's nothing to restore it. It's never going to come back. It's just going to repel forever. But with a linear restoring force, we can write this now as minus k little q big Q x divided by x squared plus r squared to the 3/2 power. And then we can say that in the limit, as x gets smaller, not completely going to 0, but in the limit as it gets small, x much, much less than r. We'll write it that way, just so we don't think that we're actually going to 0. Then we can write this as minus k little q big Q x over r to what power? Third power, right, because the x squared term is gone, and so you've got r squared to the 3/2 power is r cubed. And so sure enough, That's going to be minus k little q big Q over r cubed times x. And so this is our spring constant k. That's another k. Unfortunately, we've got the Coulomb constant in there too. But this is some other spring constant k. So if that's the case, then we know how this is going to work out. Because omega squared is equal to our spring constant over m. And so this gives us then the frequency of simple harmonic motion. And this looks like A, where A is some number that is small in relationship to R, times the cosine of omega, which is going to be square root of spring constant over the mass times t. So we've shown then that we have simple harmonic motion, that this thing will oscillate back and forth with an angular frequency, omega. It has a restoring force, it's negative, and it's linear restoring force in the limit as when x is small in relationship to r. Now it won't be true if we go out here. Go out here, then the k value is not a constant anymore, but it's a function of x. So that's not simple harmonic motion anymore. We can't describe it in terms of an angular frequency that looks like that. Any questions about that?
Your m is mass, right?
Uh-huh, right.
And that would be incredibly small for us, right? It would be like,
Well, it depends. This could be an electron. Then you'd have a small mass.
right.
But it could be an antiproton, just depending on the situation. Be less likely to be that. You know, there are a lot of other negative particles that could describe that. So what I've done here is hope that you got that, because that's going to be one of your bonus problems here. Is to write that all up and make it look pretty. Okay, so this is a bonus problem. Field along the axis, find the omega, and then what we're going to do is this next thing. This is the next part of the bonus problem. Now what I want to do, because I'm not satisfied with just a ring problem, I'd like to see, well, what could we do with the disk? And could we think of the disk somehow as being an infinite combination of thin rings? So now we're getting to a two-dimensional distribution of charge. Before we had a one-dimensional distribution of charge. Now it's two-dimensional. Increased our dimensionality by 1. And so there's a new kind of charge density that we need to look at that'll help us understand this. And that's called the sigma, or charge per unit area. This up. So this is our next task then. Let's use the result for a ring. To get E for a disk. So E for a disk is going to have to be a sum of all the E's for the thin rings. So in other words, I can take a little thin ring here, I could take another thin ring there, another thin ring there, another thin ring there, and each one of them is going to have just a thickness that's dr. And if I know what the result is for the electric field for a ring, then I should be able to get the dE for a thin ring, because a thin ring is only going to have a small amount of the total charge. dQ is the charge on each thin ring. But it is distributed over an area. And so we'll define sigma as being charge per unit area. And if sigma is constant, now there are a lot of situations that you could run into where sigma isn't constant, but I think these problems are tough enough, so at least for the time being, I'm going to keep the sigma values constant. I know that sometimes you might see in a problem-solving session somewhere a sigma value that is a function of r or something like that. And we might get to that a little later on, but I think that it's too soon to introduce that extra complication. And so for our purposes here, we'll set sigma charge over area equal to a constant. And then later on, we can see, well, what might happen if we let it vary so that it's more dense in the center and then less dense, for example, toward the outside. Okay, so what do we need to do then? Well, we need to write dE in terms of dQ. Okay, so I'm just going to put little d's in front of the e here. K dQ x divided by x squared plus, and in this case, I'll make this a squared to the 3/2 power. So in other words, this radius of the thin disk is a, then it'll eventually integrate out to a maximum radius of big R. Okay, and so this is then just the extension of this for a little tiny bit of charge in the thin ring. Does everybody see that so far? Okay, so the question then is, well, how do we sum up all these little dEs? And the answer is we're going to have to sum up a bunch of thin rings to do that. And so in order to do that, we have the integral of dE is going to be the integral of k dQ x over x squared plus a squared to the 3/2 power. Now, instead of making this a, I think I'm going to make it, no. See, I run out of symbols. We could call it R, but then we've already got this R, and then we've got this R. Just leave it A. Okay. So then how do we write this in terms of, because this is an integral, but our integration variable is dQ, and so somehow we want to write that as a function of A, right? Because the A values are going to keep changing as we sum up the different rings from 0 to big A. So what we can do then is we can say, well, charge density, big Q over big area. So that's big Q divided by pi big R squared. Okay, so that's just the amount of charge smeared out over the area. So for example here, if Q were equal to 10 to the minus 5 coulombs and R was equal to 1 meter, then sigma would be equal to 10 to the minus 5 over pi, and that would be in units of coulomb per meter squared. And so if that's the case then we could say, well, what happens if we cut the area in half, how would that change sigma? If I just go to half of the area instead of the whole area, how is sigma going to change?
The same.
It's going to stay the same, isn't it? Because the charge per unit area is the same. That means the concentration of charge is uniform over the whole thing. And so I could cut it by half, I could cut it by a quarter, or I could, in general, say this is delta Q, delta A, in the limit as delta A goes to 0. And then that just becomes dq over dA. So this is exactly the same thing I did with the linear charge density. Remember I said with the linear charge density, that was Q over L, but that was also equal to dq dx or dy, whatever the integration variable was. And so we can use that same kind of line of reasoning here. Well, the area is the area of a circle. So the area then is going to be pi a squared. So dA is going to be 2 pi a dA, where a is this little radius. I'm going to call this r. I think it's just too confusing. I'm going to call this little r, and then forget about this r. And I'll make this r. Yeah, that fixes it. And then r. So I'm calling this r just because there's too many levels of abstraction if I start calling that a. So, but dA, 2 pi r dr, how do we know that? Well, because dA dr is just the circumference of a circle, 2 pi r. Did you ever learn that in calculus? How the derivative of the area is the circumference? You kind of remember that? And then you could do the same thing for volume. You could say dV for a sphere, dr, is the area of a sphere, so it's 4 pi r squared. That's d by dr of 4/3 pi r cubed. So the derivative of the volume is the area, if you're talking about a sphere, and the derivative of the area is the circumference. So we could then just rewrite that as dA is 2 pi r dr. And then that goes in here for dA. So this is dq divided by dA, which is 2 pi r dr. Any questions so far? Now, if you don't believe that, you can just snip one of these things off, stretch it out, and then this distance is going to be 2 pi r. The thickness here is going to be dr. So it's just the area of a rectangle, 2 pi r dr. So that's your little bit of area. Okay, so once we've got that, now we're in a position to write dq as a function of r. Okay. But this r that I'm talking about here, I don't want to make it confusing. This r is the varying radius here, and we'll call this some other super big r, but we don't really need that in the problem anyway, because we already worked that out for a ring in the previous problem. So in other words, we've got this expression, we just changed the q into a dq. And so now I'm just going to relabel that radius here, little r. And I'm going to integrate from 0 to big R. Okay, so the integral then is going to be k. And then, well, where's the dq then? dq is equal to sigma dA. So that's going to be sigma times 2 pi r dr. So that's what goes in for dq into this slot. And now can you see that I can integrate over r? I can integrate r from 0 to big R. So that's the important part of that. So this is going to be sigma 2 pi r dr times x over x squared plus r squared to the 3 halves power. Okay, so that's just a little bit of charge now that's in this little area of ring. Okay, there's a total charge big Q. This is the little tiny bit of charge in that little tiny ring. But I've written it now as a function of R. So that's really good. The X we can think of as being constant in this problem, simply because I'm not varying X. My goal here is to find the electric field as a function of X at some distance X away for the disk. Okay, and so X is not varying here, but for a particular value of X, I'm making the R's vary from 0 to big R. Like that. And so that's my integral. Is that something that we can integrate, or is that too hard to integrate? I think we can do it, can't we? Okay, so what do we do with this on the bottom? What would we let that equal? U. Good. So we use some kind of a substitution then. U du substitution. Let U equal x squared plus r squared. Then du is going to be what? 2r dr. Is everybody with me? You can do this, right? In your calculus class? 2r dr. Okay, so now I'm going to write this then as the integral of du over u to the what power? 3 halves. Yeah. So let's go up here. E then is going to be, well, I'm going to pull out some constants. I'm going to keep the 2, because I need the 2 for my du. So I'm going to keep the 2r dr. But I'm going to pull out the k, the sigma. Now you could write sigma as total charge over total area at this point. But don't do it, because then you're going to confuse the r's. Leave it as sigma until the end. Then at the end, if you need to, you can plug in what sigma is. Okay, and then we got a pi. And we have an x. Like that. And then we've got the integral. Now it's an integral over u, du over u to the 3 halves power. Now I'm not going to figure out what u is being integrated between. But I'm going to just say here from little r equals 0 to big R. Because after I do the integral, I'm going to transform back into what u is equal to. Here. I'm going to put back in what u is once I'm done. Okay, so what is the integral of this du over u to the 3 halves? U to the 3 minus 3 halves power plus 1 divided by what? Minus 1/2, or that's minus 2 over square root of u. Does that look okay? So this is minus 2 over square root of u. So I'll put the 2 out front. there's a minus sign here, e, and then I'm going to have 1 over root of x squared plus r squared, evaluated from r equals 0 to big R. Everybody okay with what I just did there? I just put in what u is again. I pulled the 2 back out and the minus here. And so when r equals 0, then this is going to be divided by minus 1. So it's minus 2 over 3. Okay. So let's just write this out now as 2 going to be 2 pi k sigma times 1 over, and then I'm going to put this one in first. So that's going to be 1 over, that's going to be x. That'll be 1 over x. Because when r is 0, this is just x. Minus 1 over square root x squared plus big R squared. So I evaluated r at big R, and then I just reversed the order of the evaluation of the integral to get rid of the minus sign. Is everybody okay with that? Did I go too fast? Okay. This is just math from here, but I mean there is a little bit of math going on. So here I just said, well, this is the same thing as plus this, but integrated from 0 to big R. That's the same thing. Okay. And so this is my answer then. 2 pi k sigma x times 1 over x minus 1 over x squared minus r squared. So I could plug in any value for x and r that I want, and I could get an electric field at any distance x away that I want to. Okay, so let's just review what we did. We went through, we had our original expression for E for a ring. That was k big Q x over x squared plus r squared to the 3/2 power, and some unit vector in the i-hat direction. Then we changed the q to a dq, and then we turned the dq into a sigma times 2 pi r dr. We now have a single integral that can be evaluated from r equals 0 to r equals big R. And this gives us our final result for the electric field. Now, one particularly interesting version of this is an infinite plane of charge. We don't often need the expression for a disk, but something that is really interesting because we use it in capacitors a lot and in deflection, grid plates and stuff is the infinite plane of charge. And so how can we turn this into an infinite plane of charge?
They just integrate from 0 to
Right, or in this expression, since we've got it already in terms of r, what do we do to this expression? Just set r equal to infinity, and then we've got the expression for an infinite plane of charge. So in the limit then, as r goes to infinity, that's the radius of the disk, we have an infinite plane of charge. So we just keep expanding that radius. Then in the limit, as r goes to infinity, then E then approaches 2 pi k sigma times x over x, because that last term drops out. Or 2 pi k k sigma. And so what's interesting about this is if sigma is a constant, then E is a constant. So remember when I said before that the electric field for an infinite plane of charge is a constant value? We use that to do projectile paths of electrons and stuff. We just proved it. And so the fact that it's a constant may seem a little funny to you, though, because it seems like if you go farther away, you're getting farther away from the charges. So why wouldn't the electric field drop if you're getting farther away from the charges? Well, if you're close in, let's just take a look at a couple of dq charge elements that are nearby. They're going to set up d's like that. And if they're on equal distances on either side, the horizontal components are going to cancel, and the vertical components are going to add. Okay. What if you go out to here? Well, here, you have more of the vertical components adding for the nearby charges. But for the more distant charges, you have the horizontal components are pretty much canceling out. Okay? And so when you get in closer like this, the effects of the charges that are nearby, if you're really in close like that, the horizontal components completely cancel, and only the vertical components add. But when you get out far enough, then you have more of the vertical components adding, but the horizontal components tend to cancel. And so those two effects, it's not obvious, but those two effects just exactly cancel. So that the farther out you go, you're getting out to infinity, you're getting these effects due to these charges that more than make up for the fact that they're farther away from the fact that you're getting more of the vertical component. Whereas these charges that are really nearby, their horizontal components are almost the whole thing. Okay, and so they cancel out. And so it just, mathematically, we just showed it's true. Might not have been obvious, but the electric field, you go all the way to infinity, and the electric field is still the same. Question?
Is there a way to integrate it, the plane, infinite plane, as a rectangular, like as rectangular instead of as circular, so that way you don't have pi? Or would you end up still with having pi in the constant?
You can do it, and I'll show you how you can do it for a line of charge. Then you could add two lines of charge together. But it turns out to be a little more algebraic that way. It's more natural to do it for the kinds of problems that we're looking at here with spherical symmetry.
Would you get the same answer though, or would it be different?
You would.
Oh.
You would. And it would just be a more difficult way to approach the problem mathematically. Okay, so that's kind of interesting then. So if this is the case, then what would it be? 2 pi k sigma. Let's say sigma is equal to 10 to the minus 7 coulombs per meter squared. And k, we know, is 9 times 10 to the 9 Newton meters squared per coulomb squared. So for this problem then, the electric field at any point in the space would be 6.28, which is 2 pi, times k, 9 times 10 to the 9, times 10 to the minus 7. So that'd be 6.28 times 9 times 10 to the 2, and that would be newtons per coulomb. And so we could go in real close, or we could move out really far away, and it would be the same. that would give us 56, 5.65 times 10 to the 3. Per coulomb. So if you're in here, it'd be 5.65 times 10 to the 3. If you're up here, 5.65 times 10 to the 3. If you're down there, 5.65 times 10 to the 3. Because it's always pointing away if this is positive, from positive. Down here, same thing. 5.65 times 10 to the 3. Same everywhere in the space, but pointed straight away. So this would be some unit normal from the surface in either direction. So it'd be times some unit normal vector that points straight away from the positive. Okay, now what if it were negative? Then what would it look like?
Point towards that plane.
It would be pointed toward it, yeah. Say it had the same charge density. Then it'd be pointed this way toward negative. Like that. And so what would happen if we had positive and negative? Like this. So this is positive, this is negative, but these aren't infinite, so how do we deal with that? Well, if this distance d is small, in relationship to this length here, L, we can treat it as semi-infinite. So it's not really infinite, but it's close enough to being infinite so that we can use our infinite relationship and not have too much of an error. And so what would the electric field be in here? Due to both of those.
Point upwards.
Point up for the first one. What about for the for plane 1? What about for the second one? Same thing, right? And so what would the strength of it be if the charge density was the same as what we had in the last example?
Double.
It would be double. So this would be 2 times 5.65 times 10 to the 3 Newton per coulomb. So that would be our electric field, and it would point from positive to negative. So we could then draw our electric field lines. Remember, electric field lines are associated with intensity, the spacing of them. So if the intensity stays the same, that means the spacing of the electric field lines also stays the same. So we have equally spaced electric field lines, and where this gets messed up is out near the edges. We have some edge effects, and this is where our approximation breaks down, if D is comparable to L. Okay, but as long as D is much smaller than L, then we don't have to worry about that, and we have essentially just a uniform electric field in this region of space. Now, what would the electric field be up here, on top? Be 0, good, because you'd be pointing toward negative here. This would be E2. And this would be E1. That'd be pointing away from positive. It's farther away, but who cares? It's always the same magnitude, no matter how far away you are. And then similarly down here, this would be your E1. This would be your E2. E2 would point toward negative, the E1 would point away from positive. So the electric field is 0 here, and 0 here, and double in here. Now we can use electric fields to store electrical energy, and so that's the whole thing with a capacitor that we'll be dealing with later on as an application for this. But for the moment, these are the main points that I want to drive home from this section. Are there any questions about that? Yeah.
Yeah, so for the charge that's above, like it's outside, it's above the...
There's no charge up there. I'm talking
okay.
about the
Sorry,
electric
sorry.
field.
The electric
field, if you were to take that point and go higher and higher, that the assumption that the charge is the same would break down, right? Because it's not actually infinite. Because you said you had.
Yes. Yeah. You're going to get, but where it's going to break down is near the edges here. You get far enough away, and this is just going to look like a positive and a negative charge that are right on top of each other. So it'll still be 0 out here, but where the approximation breaks down is where you get the edge effects in here. So if you get far enough away, then this doesn't even look like a plate anymore, it just looks like a charge. And then you're super far away on Mars here, and so this distance is insignificant, and so it's like two charges that are right on top of each other and have the exact same but equal and opposite electric fields. So that doesn't break the approximation down, it actually makes it even more zero.
Makes sense.
Yeah. Any other questions? All right. Next, and let me just point out to you here that I'm wanting you to work the details of this through on this bonus problem. This is for extra credit again. That's on page 2 or 3 of that handout that I gave you. I just want you to work this back through, basically do what I did. But if you want to do well on the exam, don't just copy down what I did. See if you can do it first. And then see what problems you ran into. And then fill it in. But you should be able to do it because I did it in class. All right. Next. Okay, so we've looked at all of that. We looked at this before last time. This was for a charged rod where we were a distance d away from the edge of the rod. So that's just this calculation here that I did where all the e's point in the same direction. That's kind of a fortuitous alignment of the lines. And so what we might be interested in instead is what happens if this is a finite line of charge and we're along this axis, this symmetry axis that goes through the center of the line of charge. If we have this kind of a configuration, so before what we were doing is we were figuring out the electric field down here or up there at a distance d away. But now we're going to move out to this midpoint between the two. And so we'll call this length here, just for simplicity, 2a. And let's find the electric field at a distance x away. This is our picture. For distance x away, we've got a total length here of 2a and a total charge big Q. We find E a distance x along the axis that goes between the two. And so let's go to the handout. Here. And we can see what we're dealing with. Okay, so these are the mathematical details of how we proceed. But notice here that we've got a little bit of a complication over what we had before. We were figuring the electric field along this line. We figured it out along that line. All the DQs added up to give us DEs that pointed in the same direction. But here we've got, not only are we different, the DQs are not only different distances away from the point X, but also we've got components that are adding and canceling. So we got both things happening at once. So this then becomes a little more challenging because we got to keep track of the fact that each one of these DQs is farther away, and that each one of the DEs only has a cosine theta component that's going to reinforce. So both of those together, we're going to have to figure this out. So what do we always do in these problems? Well, we start by putting a DQ at some random position. Instead of random, I'll say representative position. Sounds better than random. Okay, so I'm going to say, okay, well, I've got this DQ there. What is that going to do? Well, that's going to shoot off a DE that points straight away from that DQ. If this distance is x, I'll call this distance y here. And so therefore, the distance away, r, is going to be the square root of x squared plus y squared. Okay, so what we could do then is say, well, okay, great. Then E equals integral of dE cosine theta. Now, before, when we were doing the curve things, we wrote everything in terms of theta. And that's because all the r values were the same. But in this case, the r values are not all the same. With that curve problem, all the r values were the same distance away, and so it was easy just to write it as an integral over theta. And we can still do it that way. But what I'm going to do is write everything in terms of x and y, because it looks more Cartesian to me. It looks more x and y than it does r and theta. Just the geometry of the situation. This looks like a y-axis. This looks like an x-axis. So I'm going to guess here that an xy coordinate system is going to be less mathematically challenging than a polar coordinate system. Okay, and so I'll write this in dE. What that is going to be, that's going to be k dq over r squared times the cosine of theta. But what's dq? Well, we learned how to do that before. dq dy is what we'll call lambda. That's also total charge over total length, q over 2a. So anytime that I need to get lambda, I can just go back. Assuming I'm given the total charge and the total length, I can get the lambda back again. But I'm going to leave it in terms of lambda. And I'll write this then as dq equals lambda dy. Now why dy instead of dx? Well, it's just because this is the way I've turned this thing. If I turned it horizontally like this, then I'd be wanting dx's. This would be lambda dx. And then this distance here would be y. So all the x's would become y's, all the y's would become x's. We're not doing it that way. Question?
Can you explain why you put cosine theta?
Oh, what I'm looking again for here are symmetries. And so in a number of the other problems we looked at, we saw that the dE, if we found a complementary dq, that was an equal angular distance on the other side, that the vertical components would cancel and the horizontal components would add. And so we're seeing that as a common theme here. We did that with the ring problem. We did it with the curved arc problem. And we're doing it here too. It's just one of those things that turns out to be a handy symmetry. And so, that if weren't at the center, can you see that you'd have a problem with just saying this is the total electric field? Because then the y components wouldn't cancel. Okay? And so that's a slightly more challenging problem, and so that's why I gave you that one as a challenge problem this week. That one is this one here. I go off the axis in this challenge problem. That I think the first thing to do is figure out how to do it on the axis. Once we have it on the axis, then I think we can see that with just a change in our integration variable, we can get the off-axis. But then we're also going to need another component, because the y components won't cancel. So that means we'll have two integrations instead of one. Okay, so any other questions so far? Okay, so we've got the dE cosine theta, and the dE is k dq over r squared. R, so I'm not going to plug this in as dq is a function of theta here. I'm going to write dq as a function of y. Okay, so r then is the square root of x squared plus y squared. Cosine theta is adjacent over hypotenuse, so that's x over the square root of x squared plus y squared. And dq is equal to lambda dy. So those are my three substitutions that are going to go into that expression, and then we're going to need to perform the integration. Okay, so I kind of skipped over that here. I went a little fast through that. And so I'm doing it slower here before. So let's pop all that in and see what we get. Well, this is going to be now, first we've got to get our minds together. What's our integration variable? What are our limits of integration? So I'm going to wait to do that. I know some of you are just really good at this, but I'm going to wait to do that for a second because I've got to pull my head together here. This is going to be k lambda dy divided by x squared plus y squared times the cosine of theta, which is x over the square root of x squared plus y squared. Okay, so I can see now, okay, sure enough, this is going to be an integral over y. So we could say this is going to be from y equals minus a to plus a, because that's where I'm going here. I made this 2a so that I don't have a bunch of a over 2's. If I made this just a, then you'd have a lot of halves in here that get squared and stuff. So it's just easier to make this twice this distance when you do the math, just from having done it before I know that. And so now I can pull out the constants. And so this is something that I've noticed a lot on exams. People will get to this point and just kind of everything fuzzes out and they start integrating with respect to the wrong variable. Okay. Remember that it's y that we're adding up. And so this needs to make sense to you. We're adding up each one of these little increments, and it's a function of y. And it's y that makes the r change, too, because the x is staying constant the whole time. So you would never integrate this with respect to x. You have to integrate with respect to y. It doesn't make any sense to integrate with respect to x. So you identify your integration variable, and then you can see that the other things are constants. K lambda x, then we have the integral of dy over x squared plus y squared. And we see this a lot, where it ends up being the 3/2 power. Because usually you'll have an r squared, which is like to the 2/2 power of some hypotenuse thing. That's your r. So your r is going to be like a square root of something squared, but then you'll have a component which will bring in another factor of square root. So that's why you're always getting that 3/2 power in there. And so now we need to integrate this. Well, in the last example, we could set u equal to x squared plus y squared, and du then would just be 2y dy. But what's the problem here with doing it that way?
There's nothing in the numerator.
No y. Shoot. You know when that happens. No y. Okay, so what do we do with that? Well, we can do a trig sub. And so with trigonometric substitution, even though I said that Cartesian coordinates are kind of the best way of going about this, to actually perform the integral, we need to go back to theta. Okay, and so if we say y over x, that's tangent of theta, right? Just from, so we can set y equal to x tangent theta, and then dy is x secant squared theta d theta, because the derivative of tangent is secant squared. So then I can plug that in. I've got my x already here, so that's okay. That's my dy now. So that's going to be x secant squared theta d theta, and then in the denominator, I'm going to write this as x squared plus x squared tangent squared theta. So that's just x squared times 1 plus tangent squared theta. That's x squared times secant squared theta. Right? So that's what I've got here then, is x squared secant squared theta, but it's to the 3/2 power. Okay, so that's going to be x cubed secant cubed theta. This is x squared secant squared theta to the 3/2. So that's x cubed secant cubed theta. Once we've got that, then it actually works out kind of nicely. Because the secant cubed cancels out a secant squared, and x cubed cancels out an x squared. So we just get k lambda over x times 1 over secant, which is cosine. And the integral of cosine is minus sign? No, it's a plus sign. The derivative of cosine is minus sign. But when you integrate, it is the opposite. So it's what was plus is minus, what's minus is plus. So it's plus cosine. So that'll give me k lambda over x times the sine of theta. And so if I wanted to here, let's say instead of just having this be a finite line of charge, I wanted to make it an infinite line of charge. Because just like with the disk, we might, instead of wanting a disk, we might want an infinite plane of charge. An infinite line of charge, we can make semi-infinite in certain situations. So an infinite line of charge might be interesting to us. And so for an infinite line of charge, we can just integrate the sine of theta from minus pi over 2 to plus pi over 2, because this thing goes all the way down to infinity, so that becomes minus pi over 2. And then when it goes all the way up to infinity, then on the top side it becomes just plus pi over 2. So that just gives you a 2 here. So you have the sine of pi over 2 minus a negative 1, so it's 2 k lambda over x. So that's the result then for an infinite line of charge. 2k lambda over x. And we, in a way, we kind of did it the hard way, because in chapter 23, when we do Gauss's law, we'll do it in one step. Instead of having all this stuff that we have to do, we can do it in one step, but we have to understand the idea of electric flux. for that to work for us. Okay, so that's the infinite line of charge. But let's go back to the finite line. So I just kind of did this as a little aside here, because I thought it was fun. Hang on. Who would think that's? But now, for shorter a distances, we can't just integrate from minus pi over 2 to plus pi over 2. It's going to be hard for me to see how sine theta relates to a unless I plug it back in. And so what's the sine of theta? Well, we know what the sine of theta is. Sine of theta is just like this. This is just y x square root of x squared plus y squared. So we can plug back in what sine theta is from our reference triangle. This is our reference triangle. Remember, this was the total length of this thing, and this was the distance x away. So we're just going right back to our reference triangle. When you learn this stuff in calculus, they don't ever put it in terms of physical terms. They just go, just remember to do it that way. But here you can see what the transformations are actually representing. I think that makes it easier to understand. So if we plug that in for sine of theta, then we're evaluating between y equals minus a and plus a. Okay, so we just have this expression here, but by putting it back in terms of y and x, we can then see